Welcome to Homeschool Connections Chemistry Lab. Today we're going to be discussing your Titration Lab. A titration is a lab technique in which you use a solution with a known concentration to help you determine the concentration of another solution. In today's lab, we are going to be doing an acid-base titration. We will concentration of our sodium hydroxide, and we will use that sodium hydroxide to help us determine the concentration of acetic acid in vinegar. And we are going to be able to determine that concentration using two different units. First, molarity, and then second, percent acid in the vinegar. Let's look at a couple acid-base reactions. First, hydrofluoric acid plus potassium hydroxide reacting to form water, and the salt potassium fluoride. Notice it takes 1 mole of acid plus 1 mole of base to form that water and potassium fluoride. Let's look at that second equation there. It takes 2 phosphoric acids plus 3 magnesium hydroxides to form 6 waters and the salt magnesium phosphate. This initially does not look like it's reacting in a 1-to-1 mole ratio, but if we look at how it ionizes in water, we can easily see that the phosphoric acid will ionize to form 6 hydrogen ions, 6 moles of acid, and the magnesium hydroxide will ionize to form 6 hydroxide molecules, 6 moles of base. So it again reacts our acid and bases in a 1-to-1 mole ratio. You've probably also noticed that our acids and bases always react to produce water and a salt. So now we know in acid-base reactions, the moles of acid reacting is going to equal the moles of base. Let's recall the definition for molarity. Molarity equals moles per liter. When we combine these two equations, we get a very important equation. The molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. This is going to prove to be a very, very useful equation for you. Let's use that equation to calculate the molarity of an unknown solution. We're going to be using that chemical reaction hydrofluoric acid plus potassium hydroxide going to water and hydrofluoric acid. If it takes 5 mils of 1.5 molar hydrofluoric acid to neutralize 44 mils of potassium hydroxide, what is the molarity of the potassium hydroxide? Well, we can drop our knowns into the equation. The molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. What we're looking for is that molarity of the base. We knew the molarity of the acid we were using. We knew the volume of the base we were using. We measured the volume of the acid, plug those values into the equation, and do the math, and we find that the molarity of our base is 0.17 molar. Let's take that example one step farther and calculate the percent of potassium hydroxide in that solution. To do this, we are going to assume that the density of the solution is 1 gram equals 1 ml. So we know the molarity of our solution, that is 0.17 moles per liter. We need to get that in grams per liter, so we multiply by the molar mass of potassium hydroxide, which happens to be 56.09 grams per mole. So we know that in a liter, we would have 95.4 grams of potassium hydroxide. When we're doing percent, we need to have it in grams per milliliter. So we do that calculation, that unit conversion, multiply by 100, and we find that we have a 9.54% solution of sodium hydroxide. Well, now we know how to do the math for this lab, but how are we going to perform it? Well, this titration is a 3-step process. First, we're going to measure out a known volume of our acid, of our vinegar, and we are going to put that into one of the wells of our reaction plate. To that, we are going to add an appropriate indicator, and then we are going to take our base that we know the concentration of, and we are going to slowly add it to that acid, drop by drop, and we're going to be counting as we go. And we're going to do that until our indicator changes color. Notice in step 1 we get our volume, and in step 3 we know our molarity of our base, and we measure the volume of our base, and that leaves only the molarity of the acid as our unknown. I said we needed to add an appropriate indicator. Well, what exactly is an indicator? Well, it is a substance that has one color in an acidic solution and a different color in a basic solution. If you look at our graphic here, we see a number of different indicators and what color they are at what pH. For our reaction, we are going to be using phenolphthalein, and if we look at the graphic, we can see that it turns from the clear in the acid solution to the pink in a basic solution, someplace between a pH of 8 to 10. Okay, when we are doing the titration and our solution with one drop changes from clear to pink, that is the end point of our reaction. The equivalency point is when the moles of acid equal the moles of base. If we have picked an appropriate indicator, our endpoint and our equivalency point will be very close to each other, if not equal. If we were to plot the pH of our solution versus the number of drops of sodium hydroxide added, we would get what is called a titration curve. Notice in the lower left-hand corner of the titration curve, our pH is about 2.8. That is the pH of the acetic acid. Notice as we add sodium hydroxide, the pH slowly increases until we reach about 25 drops. That first area there, we have an acidic solution, and our hydrogen ion concentration is greater than our hydroxide ion concentration. At about 25 drops, we have a very sharp increase, and with that very next drop, we are in the basic range, and our hydrogen ion concentration is now less than our hydroxide ion concentration. Where we have that sharp increase is called our equivalency point. That is the point where our hydrogen ion concentration equals our hydroxide ion concentration. Notice I have in a box where our phenolphthalein changes from clear to pink. And our equivalency point is right in that box. So this is a good indicator for this lab. And that will be the indicator that you will be using. We're going to start this lab the same way we start all our good labs, and that is with a hypothesis. This hypothesis is going to read, by titrating a known volume of vinegar with a 0.1 molar sodium hydroxide solution, a base, the blank of the acetic acid in the vinegar can be calculated using units of blank and blank. The next line reads, the percent acetic acid in vinegar will be. Now this is not a wild guess. We never wild guess in science. You're going to take your bottle of vinegar, and someplace on that front label it will say percent acid or percent acetic acid, and that is what you anticipate that you will calculate your percent acetic acid as. Notice this line here also gives us a little clue as to one of those two blanks for units up there. Do you think percentage might be one of those units? In this lab, I have written out your materials and procedure for this lab. You are not going to be using your lab manual. In the materials section, though, there is one thing you need to fill out, and that is about your vinegar. Now, make sure you use a clear vinegar. That way you can see when the phenolphthalein changes color. You most definitely don't want anything like a red wine vinegar, and you probably don't even want a cider vinegar. A nice clear vinegar will make this lab easier for you. I need you to tell me what brand of vinegar you're using, and I need you to write in the percent acid from the label on this line. Now let's go down to my kitchen and perform this lab. We are now down in my kitchen lab, and I'm getting ready to demo the titration lab for you. The first thing that we need to know for this lab, though, is the volume of 1 drop of solution. To do that, we are going to use a beaker, and we are going to count the number of drops it takes to reach 1 milliliter. Now remember, 1 milliliter equals 1 gram, so we can weigh this. So let's start there. First thing we need to do is put our beaker on the scale and turn our scale on. If we put our beaker on first before turning it on, it is likely to come up reading 0.00. If it does not, press the tare button. Now, we need to carefully drop in our water, counting the number of drops until we reach 1 gram. 1, 2, 3, 4, 5. To do the titration, you need to start with a vinegar. And on the label, you will see a place where it will say percent acid or percent acetic acid. Be sure to record that both as part of your hypothesis and in your materials section. As you can see, my bottle is about empty, so I am just going to pour a little bit of vinegar into another container, and I'm going to use the vinegar from here. Now, the vinegar in this bottle is too concentrated for us to do a titration with, so we are going to need to do a 1 to 10 dilution. To do the dilution, you put a beaker on the scale again and turn it on, and it should read 0.0. Next, we are going to need to add 2 mils of our vinegar. I am going to do that with a pipette, a graduated pipette. Notice this is 0.25 mils, 0.5 mLs, 0.75 mLs, and this is 1 ml. Though we're going to measure it on here, we're just going to read 2 grams. It's a good idea to start trying to read exactly 1 ml because later in this experiment it's going to be important. So let me see if I can pull up exactly 1 ml and add to it. And I was close, 0.91. I'm going to try again. Okay, I'm at 1.83 ml, so I need actually just a little bit more. I'm going to add it by drops until I get to 2 mLs. Okay, I'm at 1.97. I know if I add another drop, I'm going to go over, so I'm just going to leave it there. And now I have got to dilute this to 20 mLs. Okay, this is a good time to keep practicing. I'm pulling up exactly 1 ml. Okay, you need to take it up to 20 mLs. Okay, I am now at 19.61 mLs. This is a good time to start adding water just drop by drop until I get to 20 mLs. Wow, absolutely right on. And now we have our 1 to 10 dilution of our acetic acid. This is what we're going to be using in our experiment. To do the titration, you're going to want to set your reaction plate on white paper. Remember, we're using the indicator phenolphthalein. It's clear in an acid solution, but it is pink in a basic solution. We need to clearly be able to see that color change. In wells D1, D2, and D3, each of them we're going to add exactly 1 ml of our diluted acid. Okay, we are going to use that same pipette. 1 ml into D1. 1 ml into D2, and another ml into D3. Okay, it is very important that you add exactly 1 milliliter here. This is going to be the volume of acid when we're calculating the molarity of the acid. The next thing you want to do is add your indicator. You have a phenolphthalein strip, and you need to add just about maybe 5 milliliters, a little bit less, to each of these wells. Okay, it doesn't take much indicator paper to be able to see that color change. Okay, and then kind of swirl it, get it wet in there. And now we are going to titrate well D1. We are going to use our 1 molar sodium hydroxide. We are going to want to hold the bottle absolutely vertical and count the number of drops that it takes to turn it pink. 1, 2, 3. Oh, our paper is pink. But notice as soon as we stir this, that pink goes. Okay, so that was 3, 4, 5, 6. Let's see if this is going to stay. No, but it's getting close. We probably want to do 1 drop at a time now. 1 drop, stir. You do it both two-handed. You can do drop. Oh, we're getting close. It's staying a little bit longer. Okay, we are now pink, and as much as I stir, it does not go away. So I record the number of drops it took me to get there, and I do the exact same thing in well D2 and in well D3. Okay, you notice how it went from absolutely clear to pink in 1 drop. You want to be very careful that you know exactly how many drops it took to get there. And now we have all the data we need to calculate the molarity and the percent acid in our vinegar. So after cleaning everything up, we'll meet again in our classroom. We are now back in the classroom ready to do our calculations. What you see in front of you is the data I collected when I was demoing this lab. In Table 1, we have the drops of water that it took to reach 1 ml, or I should say 1 gram, because 1 gram equals 1 ml when we use the scale. In Trial 1, it took 22 drops, Trial 2, 23, Trial 3, 22 drops. When we average them together, add the 3, divide by 3, I find my average was 22.3 drops per mil. Drops per mil is not a useful value for us. What we really need is how many mils there were in every drop, the volume of 1 drop. And to do that, we just take 1 ml divided by our number of drops, and I find that I had 0.045 mils per drop. That number is going to prove important later on. In Table 2, we see the data on how many drops of titrant, our NaOH, the base, it took to reach our end point where the color changed. In Trial 1, well D1, it took 27 drops. Trial 2 took 27 drops. In Trial 3 took 26 drops. When I average these, I find that on average it took 26.67 drops. Now, the number of drops isn't going to be useful in our equation. What we need is volume. To get this, we multiply the number of drops times the volume, the mils per drop that we just calculated, and I find that it took on average 1.19 mils of our base, NaOH, to titrate our vinegar. The first calculation we need to do is for the molarity of our diluted vinegar. In this experiment, we know that we used 1 mil of our diluted vinegar, so that's the volume of our acid, and we know that we used a 0.01 molar sodium hydroxide, that's the molarity of our base. We measured the volume of our base added, and that was 1.19 mils of sodium hydroxide. We dropped those known values into our equation. The molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base, and we find that the molarity of our diluted acid was 0.119 molar. Next, we need to do a calculation for the molarity of our undiluted vinegar. Recall in the lab we did a 1 to 10 dilution of our vinegar. So here we are going to need to multiply the molarity of our diluted vinegar by 10 to get the molarity of our undiluted vinegar, the molarity of the vinegar in our bottle. So for mine, it would be 0.119 molar times 10 to give me a 1.19 molar acetic acid in the vinegar that I used. The next calculation is for the molar mass of acetic acid, CH3COOH. We have calculated the molar mass a million times by now. Next, we need to find the mass of the acetic acid in 1 liter of our undiluted vinegar. To do this, we multiply the molarity of the undiluted acid by the molar mass of acetic acid, and if I do that calculation, I find that I have 71.70 grams per liter of acetic acid in vinegar. Now I have all the information I need to calculate the percent acid in my undiluted vinegar. I know that I had 71.70 grams of acetic acid per every liter of vinegar. To calculate percent, I need volume in milliliters, so I need to multiply by the conversion factor. 1 liter equals 1,000 milliliters, and then multiply by 100 to get percent. And I find that the vinegar I titrated was 7.17% acetic acid. Next, I need to calculate my percent error. Experimentally, I calculated that I had 7.17% acetic acid in my vinegar. The label told me that I had 7.5%. To calculate the percent error, I take the absolute value of what I calculated experimentally minus the actual, what the label says, divide by the actual, multiply by 100 so that we get percent, and my percent error was 4.40%. Now, it is quite easy to get percent errors under 10%. If you have an error of greater than 10%, you should either go back and check your math, and if you're quite certain that that's right, maybe you need to go back and re-perform that experiment, being very careful in all your measurements. One other thing I should note is that I have my acetic acid in vinegar at 7.17%. This is very high for vinegar. Most vinegars have a significantly lower percent acetic acid. Make sure that you record the percent acetic acid from the label of your vinegar. Do not use my 7.5%, otherwise you are going to have a huge percent error. Now for our conclusion. as you're writing this, please remember this is a quantitative lab. You measured, you calculated. Numbers were important throughout every step of this. We need to be sure to include those numbers in our answers. Also, it is the conclusion. Our answers need to be complete sentences. Question 1 reads, A, what is the experimental value for the molarity of the acetic acid in your vinegar? B asks, what is your experimental value for the percent acetic acid in vinegar? Okay, be sure to include the numbers you just calculated. Question 2 reads, how does the experimental percent acetic acid and the actual percent acetic acid, that's the value on your bottle, how do they compare? When you're answering this, you need to be sure to address your percent error. Question number 3 asks, what are the possible sources of experimental error in this experiment? Experimental errors are not math errors. They are things that could have happened during your experiment. Some of them you can control, some of them you may not have controlled. But these are the things that happened in your experiment that would cause your percent error to be anything other than 0%. Question 4 then asks, what could you do to minimize or eliminate those experimental errors if you could do that experiment a second time and you had unlimited budget and unlimited supplies? Okay, what other ways could you do it to get a better answer? And that is it for this lab. We'll see you again next time. God bless.